Okay, this is going to be the video for chapter 22 for AP Statistics, which is the last chapter in Unit 5, and it's about comparing two samples that each contain a proportion with each other, instead of comparing one sample against some null hypothesized value. All right, so actually comparing two proportions to each other might be more common than comparing one proportion to a historical value, because this is how you finish off, say, an experiment. If you have an experiment where you're comparing one, let me just show you real quick. Let's say that you do some kind of an experiment where you have some subjects and then you randomly assign them to two groups, and then you do some kind of treatment one over here and treatment two over here, and then you have to compare. Well, maybe you have in this group you have p hat 1, and in this group you have p hat 2. So you're not comparing a sample to some historic value. Maybe you're comparing one sample to another completely different sample. That's what this chapter is about, this comparison here between two separate samples. Okay, we're going to look at this example we've been using throughout this unit about DV seniors and what percentage of them stay in state to go to college. So let's say in the previous example, we know, say, that the DV counseling department records show that in the past, 78% of DV seniors attend college in state. We ask a sample of 200 seniors this year, and 168 of them say they're staying in state. Do we have reason to believe that more seniors are staying in state than this year, which is comparing one sample's proportion to a value from the past, right? Okay, but maybe we want to say this year, 172 of 200 seniors stayed in state, but last year 114 of 150 seniors that were sampled stayed in state. Do we have reason to believe that more are staying in state, or is this difference significant? Here we're comparing two separate samples to each other. Okay, that's a different thing, and the reason it's different is because the statistic is different, and how much that will vary is different because we have two sources of variation. Okay. Although it is possible we have a known or suspected population proportion to compare a sample to, it's actually more common that we have two samples and we want to compare them to each other. Okay, so this is what we're going to learn here. The way I'm going to show this is, since we now know all of the stuff we need to know about inference, about how to do hypotheses and confidence intervals and all that, I'm just going to do this like an analysis, and we'll do one using the single sample method that we already know on the left. And on the right, I'll show you the corresponding steps for if you're comparing two proportions to each other. So there'll be two analyses done in parallel here. And I've left them blank in the notes. Well, I guess later we'll have an example we can do together. This first one is worked out. Okay, so if we're comparing one proportion to a value, then our null hypothesis is going to be that the population P is equal to the historic value, and then the alternate hypothesis is either greater than, less than, or not equal to that same value. Okay. The difference when we're comparing two proportions to each other is that you're going to say the null hypothesis is that there's nothing to see here, there's nothing noteworthy, which would mean that the proportion populations are equal. In other words, the proportion from sample 1 in the population is equal to the proportion for sample in the population for sample 2, or that one is greater or less than or equal, not equal to the other for the alternate hypothesis. So instead of comparing a sample value to a number, we're going to compare one sample value to another sample value. So we have two different populations for each of the two samples. Or you could also bring this over to the left and say that the difference between them is 0, which is in practice how we analyze this. Or the difference is greater than 0, or the difference is less than 0, or the difference is not equal to 0. And that it matters which order you put here, because if P1 is greater, then that would lead to a positive value, whereas if P2 was greater, it would lead to a negative value. So now the hypotheses are written using two different proportions. And at this point, you pretty much have to define symbols, right? So there'll be a step before this where you define what P1 is. Like maybe P1 is the proportion of yeses in the treatment group, and P2 is the proportion of yeses in the placebo group, or something like that. All right, so we have to have some sort of a statistic to use as a boundary value, right, for computing the p-value. And for one proportion, it's just the number of successes out of the total number in the sample. So there's a single p-hat, right? But if you're comparing two proportions, like say this year's data to last year's data, then you would have a number of yeses out of a total for for this year's data, and then a number of yeses out of a number total for last year's data. So you'd have two p hats. And then what I'm interested in is the difference. So I'm going to pick one of them to be first and say the p hat for the first one minus the second one. And then we're going to effectively define a new random variable d, which is the difference of these two individual sources of variation. So the difference d is going to be equal to p d hat is going to be p1 hat minus p2 hat. So the statistic or estimate is now the difference between the proportions in the samples rather than just the proportion itself. Okay, so then we have to have a way to figure out how much will that statistic vary. So when we have a single p hat value, then we use the square root of PQ over N. That's the sampling distribution level model that shows how p hats will vary. Okay, so how is it that D's will vary since they are P1 hat minus P2 hat? Okay, how will that vary? Well, we have two sources of variation here, right? We know that if we have variation for D, and that's equal to a separate variation for P1 and a separate variation for P2, we know that the means will follow the algebra, so P1 minus P2, and then we know that the variances will add, right? The variances for the difference will equal to the variance for P1 and the variance for P2, standard deviation squared, which is why you end up with this formula here, that the standard deviation for the differences is the square root of PQ over N for 1 plus PQ over N for 2, okay? All right, so this comes from this formula here. If you follow it all the way through with standard deviation, you'll end up with this, okay? So we have a different way to, because we know that there's different, we have to combine and account for the individual variations. So we have a different formula for the standard deviation when we do a comparison of two proportions to each other. Okay, so then when we do the p-value calculation, we have to take the null hypothesis value, right, which is some historic value in the one proportion case, find our p-hat value, shade appropriately for our alternate hypothesis, like greater than is shaded to the right, and then find the p-value here, right, using normal CDF. In the case with 2, what we're using is comparing the d hats, right? This is for p hat value. This is for d hat. So the null hypothesis value is that P1 equals P2, or that P1 minus P2 is 0. In other words, the middle of this distribution will always be that there's a difference of 0, because our null hypothesis will always be that the two proportions are equal. And so using that as the middle and our calculated standard deviation, we can put our particular difference on and then find the p-value here. Okay, and we use normal CDF for that. Then when we write up our conclusion, right, we used to say things like this. With alpha equals 0.05, p, say 0.0203 is low, so we reject the null. We have sufficient evidence to conclude that the percentage of students at DV staying in state for college this year is higher than last year. But now we have a slight difference in the write-up here. The first sentence is the same, right? With alpha is 0.05, p of whatever it is, 0.0095 is low. Say if it's low, we reject the null. And therefore, we do have sufficient evidence to conclude that, but this time it'll be the percentage of DV students staying in state this year is different than last year. This year is higher, or you have to change this depending on the HA. So the thing that changes is that this wording here is about comparing the two instead of comparing the one value in the sample to a number. Okay. And if we want to know, okay, how much higher, then we provide a confidence interval. So what we're saying is, if you've determined that you're not at your null hypothesis value, right, then you take whatever value you are and you put a confidence interval around it to bound it to get a region to say, well, where is it if it's significantly different, right? So the way we would do that with a single proportion is to use this formula, that the confidence interval is our p hat in our sample plus the number of standard deviations, z star, times the size of a standard deviation. And there's the formula for that for a single proportion. There's really no difference here. It's still p hat. There's actually an error in the notes here. This would be d, right, which is the difference between the two, okay? So you could write that as d hat, or p1 minus p2, p1 hat minus p2 hat. And then the other difference is that we have to use the standard deviation formula here, which this is the square root of p1 hat q1 hat over n1 plus p2 hat q2 hat over n2. Okay, so we have a different formula here and we have a different statistic. Okay. And then, of course, we can talk about the test statistic for this versus the statistic. This is going to become more and more important as we go throughout the semester here. So the statistic is the actual value, right? In a one proportion value, right, we would have that you take your p hat value and you subtract the null hypothesis value, and then you divide by the, well, I guess that's not a hat because it's not an estimate. And then you divide by the standard error for p hats to find the number of standard deviations away. So when we do this calculation where we would do normal CDF over here, right, with the actual p, we can either use the actual p and the actual standard deviation, or we can convert something to a z-score by taking the p hat value minus the null hypothesis value over the standard deviation, and then plot that z-score on a z-score distribution. You get the same proportion, right? So what would it look like if you had two proportions? Then the z-score would be, you would have to take the difference. So p1 hat minus p2 hat, or the difference minus the difference of 0, which is the null hypothesis value, over the standard error for differences for p hats minus p1 minus p2 hat. But you would still then plot on a z-score on a z distribution, right? So this is the difference between using the test statistic, which is z-scores, or using the statistic, which is either the raw p hat or the raw difference, okay? All right. Okay, so the next thing we need to talk about is when it comes to having two samples, you can do something called pooling. And in the last analysis, we stated that the null hypothesis is P1 equals P2 because we're assuming that the difference is 0. Okay. When we did the test for one proportion, we used a standard deviation rather than a standard error because we had a known or assumed population proportion. Here, we're just using samples, so we have to use the sample value, so we have standard error. But our null hypothesis is stating that we're assuming that the two are equal. So if the two population proportions are equal, it's almost as if they were both sampled out of the same population. In other words, let's go back to the very first screen. If you had an experiment design, and yes, you divided up these into group 1 and group 2 and did some experiments, so you got a difference. But really, they ultimately came out of the same subjects groups at the beginning, right? So if that was true, then the variation might be similar between these two groups. The variation from person to person would be similar. And that's the reason why our null hypothesis is assuming these are the same, because ultimately they kind of come out of the same distribution. This doesn't have to apply only for experiments, by the way, but conceptually the thinking makes sense, right? That if you're assuming that the two proportions values of interest are equal, then it's almost like it's one big population. So what we can do is we can say, all right, we're going to have to keep the actual p hat values separate so we can measure the difference. But when it comes to analyzing how much difference we have here, we can, for the standard error, we can use an alternate formula where we're making an assumption that the samples really came from the same pool of subjects. And so whenever you can make this assumption, which you can with any hypothesis test because you're assuming this is equal, we calculate something different called the pooled p hat. Now, the pooled p hat says take however many elements there are in sample 1 and add that to sample 2 to get a total number in the combined samples, and then add the number of yeses and the number of yeses together to get a total number of yeses, right? Where I've got like a total number of yeses between the two samples over a total number in both samples together to come up with one p hat value. And then we still use this value because we're still comparing two individual samples, so they could each vary. So I still have to have that square root of the sum of the squares thing, but I'm going to use the pooled value for both of the p hat values, and then 1 minus that for q with the individual sample sizes. Okay, so this is felt to give a potentially more accurate estimate. Remember, this is an estimate of the true standard deviation, right? So we're just trying to estimate this as best we can. And in the case of hypothesis testing with two proportions, we had when I took a class from one of the AP scores here, He stated that the AP College Board expects you to do pooling whenever you're doing hypothesis tests for two sample comparisons. So we should use this alternate formula instead of this formula. When we do that. In fact, if you look at let's take a quick look at the sheet for AP Statistics, the formula sheet. See if I have it handy here. Okay, so this is the official formula sheet. If you look for proportions, it'll say for two populations. So in one population, we have the standard deviation here, and the standard error, S, is square root of p hat q hat over n. And then it shows that formula p1 hat q1 hat over n1 plus p2 hat q2 hat over n2. But then it says whenever you're assuming p1 equals p2, which is true for hypothesis tests, then you should use this alternate version where you have a combined total here. And this is just an algebraic manipulation of the one we just showed on the other screen there. Okay, so what they're really saying is AP wants you to use this formula when you're doing hypothesis tests because you're asserting this. But if you're doing a confidence interval, you should use this first, more general one, because we're not making an assertion that these two proportions are the same. Right, a subtlety, but we'll see that when we actually do some examples here. Okay, so here's an example where we're just going to rework that last problem. Okay, but we'll do this with pooling this time. So let's say that this year 172 out of 200 seniors stayed in state. Last year 114 out of 150. Do we have reason to believe that more seniors are staying in state, so we make our alternate the greater than shading? Okay, so we could calculate our P1 hat. This is P1 hat for last year, and that would be that there was let's see, 172 out of 200, which turns out to be, make sure that's the right one here. 172 out of 200 turns out to be 0.86. And then if we take 114 out of 150, we get P hat 2, which is 76%. So the difference is 10%. So we had 10% more seniors staying in state this year for college compared to last year, right? And so what I could do is say, okay, let's find a new pooled p hat value, right? Take the total of the yeses over the total of the samples and get 0.8171. That's somewhere between, it's like an average of these two values. And then when I calculate my standard error, I use that value for p and 1 minus that value for q, but I still use the original n's, sample sizes, and I compute this. Okay, and then when we calculate this over here, we get 0.0084. Let's take a quick look at well, let's do this whole thing here, and then we'll go back and I'll show you the steps to do the analysis completely by hand. All right, there are calculator functions for this as well. Just like we know that if you go to a calculator, you have under stat, and then over here for tests, you have a 1 proportion z test and a 1 proportion z interval. For example, if I look at that 1 proportion z test, it asks you to enter a null hypothesis value and then a number of yeses and a number total, and then set the direction and then calculate it, and it gives you the p-value directly and the test statistic, right? But there's also a 2 proportion z test and a 2 proportion z interval. So if you look further down, there's a 2 proportion z test, and when you click that, you have to enter the yeses and total for both sample 1 and sample 2. It doesn't have a null hypothesis proportion because the null hypothesis is assumed to be that the difference is 0. And then you can do the shading direction, P1 compared to P2. And then there's also further down, there's a 2 proportion Z interval where you enter that similar data, but this time it's calculating a confidence interval. So you set the confidence interval level. All right. And the calculator will always perform pooled values for the 2 proportions. All right, there are assumptions and conditions that you always have to check, of course. We have to have a simple random sample, a true simple random sample, or believe the samples represent the population without bias. You have to be able to assume that the true groups can vary independently of each other. So there has to be no connection between them, right? That's a new one. Now that we have two samples, we have to be able to say that they're varying independently. Before we said that there's an independent criteria, and that is that the elements within the sample have to be not affecting each other. But now, for this case, we're stating that the two groups must be able to vary independently from each other. We still have the n is less than 10% population, but now it depends on how you check it. If they really came from two completely separate populations, you'd want to check that N1 is less than 10% of this population and N2 is less than 10% of this population. But if you're going to be pooling because you're assuming they're kind of from one population, then you want to check that the total sample is less than 10% of that total population. So I've seen it done either way. It kind of depends on the context of the problem. And then there's more work to do for the success-fail criteria. You have to check NP and NQ are greater than 10 individually for each of the two proportions separately. All right. All right. So given that, let me just show you from start to finish what an analysis would look like if we just did the, let me go back to the first screen and we'll just take the problem statement for this right here, and we'll just work this one. Okay, so this is a comparison. This is how I would do this work. And I'll show it by hand and with a calculator so we have something to reference here. All right. First of all, I've got this year and then last year. So I'm going to use, I'm going to define the symbols. So I'm going to define PT to be this year. Okay, and it's going to be the percentage of DV seniors in state this year for college. Okay, and then I'm going to define a symbol called PL for last year. Okay, and that's going to be you can use quotes, except it's going to be last year for college. Okay, so I've defined symbols here, and then I'm going to use those symbols to make hypotheses. So let's write the hypotheses out. I'll do that in black. The null hypothesis will be in symbols. It'll be that PT this year's proportion of seniors staying in state is equal to last year's. Okay, or there has been, in words, no change in percentage of seniors staying in state. Okay, the direction for HA depends upon the wording. It says, do we have reason to believe that specifically more seniors are staying in state this year? So that would be this year's proportion is greater than last year's proportion. So this direction has to match the wording. Okay, and that would mean higher percentage of seniors in state this year than last. Right now, I'm asking you to write them both in words and in symbols, okay, for full credit, and define symbols. Okay, so we've got that. Now we're going to go ahead and look at what we have for our actual, what happened in the experiment. So this year, so my p hat value for this year is 172 out of the 200 seniors, right? Which would be 0.86. And then last year, we had a sample of 150 seniors taken and 114 of them stayed in state. It's not required that these match, but it turned out that 76% of the people stayed in state last year. Okay, so it does look like on the surface, more seniors, a higher percentage of seniors are staying in state this year than last year. The question is that difference significant enough for us to say that not just in the sample, but in the population as a whole, this is true. All right, so then I'm going to calculate a statistic here. It's going to be the difference, and I'm going to define the difference, D. So we're going to define D to be this year minus last year. So it's important that somewhere in the problem I define the direction. That means that my D hat is 0.86 for this year minus 0.76 for last year, which is 10%. So 10% more seniors stayed in state this year than last year. So I'm making a new single variable, which is the difference between the two. Okay. Then I'm going to have to figure out what is the standard deviation that we're going to assume here. Okay. Now, for the standard deviation of the differences because I'm doing a hypothesis test here, I'm going to calculate this making the assumption that these are the same. So according to the AP guy, I should use a pooled statistic. So I'm going to use pooling. Let me do this now. P hat pooled is going to be equal to my total number of yeses, which is 172 plus 114, over my total number in both samples. So that's going to be 172 plus 114, which is 286, over the total of 350. 286 out of 350 is 0.8171, okay? And so I'm going to use the pooled version here, which means I'm going to take the square root. It's going to be P, the pooled P, 0.8171 times 1 minus that, which is 0.1829, over this sample size 200, plus the other one, which is 0.8171. I'm going to use the same average of the pooled average, but with the other sample size. Okay, and now I'll carefully do this. Now I like to do this kind of step by step here, so let me just do it offline here. 0.8171 times 0.1829 divided by 200, and then if I add 0.8171 times 0.1829 divided by 150, and then I take the square root of that answer, I get 0.0418. Okay. If I didn't do pooling, if I used this p hat here and this p hat here, it's slightly different. In fact, let me just show that right now. So if I redid this calculation, there's two versions of this. I can use the 0.86 and 1 minus 0.86, which is 0.14 over 200. And then the separate 0.76 times 0.24 over 150, that turns out to be 0.0426. They're very close, right? So esoterically, what AP says is we're supposed to use the green pooled one when we do a hypothesis test, because we're assuming that these are equal, and we're supposed to use the red one if we're doing a confidence interval. All right, so since I'm doing a hypothesis test, I'm going to use the pooled version, okay? And now it's time to draw a picture of our sampling distribution. So the sampling distribution is going to be centered at the null hypothesis value. So the null hypothesis value is that the difference is 0, right? Because there's no difference between the two. So this is d hats and how they vary, and we assume 0. The standard error for that, the pooled one, is 0.0418, okay? And therefore, I have a particular difference, right? My particular difference was 10. So I will go out here to 10. Somewhere out here is my particular difference, which was 0.10. And then I will use that to calculate the p-value. Now I shade to the right because my null hypothesis is greater than. So my p-value is going to be normal CDF from the lower boundary 0.10 to the upper boundary of positive infinity if we assume a difference of 0 and a variation of differences of 0.0418, labeled lower, upper, mean, standard deviation every time. Okay, and then I know you know where to find this in the calculator. 0.1999, 0.0418. So we get 0.0084. And that means we have to have a conclusion paragraph that says something like this. Let me change colors here to emphasize it. We have to indicate our significance level. So we'll use the traditional 0.05. With alpha 0.05, p-value equal 0.0084 is low. So we reject the null hypothesis, and you can use the symbol there. But in the second sentence, we have to write this in context. Therefore, if we do reject, we do have sufficient statistical evidence to conclude that, and then we're going to write up our alternate hypothesis that a higher percentage of seniors are staying in state this year than last. That a higher percentage of DV seniors are staying in state for college this year compared to last year. So the writing of the alternate hypothesis and wording helps us fill out our paragraph. Okay, just reviewing what we're saying is, right, we're wondering what happens in all of the DV senior population, right? The hypotheses are about the population. We took a sample, right? The sample did show that 10% more people stayed in state in the sample this year compared to last year. But by doing the analysis and finding the p-value, we're now able to state that for all DV seniors, this is true, that a higher percentage is staying in state, okay? But we can't assert that the value, the actual difference, is the 10% we saw here. If I wanted to do that, I would have to follow this on with a confidence interval. So let's do that below here. Separate problem. Okay, well, how much higher is it? We can't use the 10% number because that was just for the people in the sample this year and last year. Okay, so if I have to answer the question, how much higher, then I have to do a confidence interval. So the confidence interval for a difference is, it's going to be the difference we saw in our sample plus or minus some standard error, number of standard deviations times the standard deviation of the differences. Okay, so in our difference, in our sample, we had a difference of 10%. We're going to use a value here. Let's say we want to be 95% confident in the result. So over on the side here, I could do a little z-score calculation. If I want 95% chance of capturing the true value, there's 5% left over, 0.025 here, 0.025 here. And then you could find this boundary value here, z star with inverse norm, and it would be 0.025 area to the left with 0 and 1 as the standard deviation. You'll get negative 1.96 and throw that away. So I have to go almost 2 standard deviations above and below to be 95% confident of capturing that value. So I'll use the 1.96 number for 95% confidence. And then I'm going to use the standard error, but because this does not include a hypothesis that we're no longer assessing or assuming that these proportions are equal, where we've concluded that this is not true. So I shouldn't say that these are sampled from the same population. So I'm not going to use the pooled value. I'm going to use this value, the non-pooled value. So 0.0426. Okay, so use the non-pooled value for confidence intervals, but use the pooled value for hypothesis tests. Okay, so I've got let's see, this is going to be 0.1 minus 1.96 times 0.0426. And that means the lower boundary here will be 0.0165. And the upper boundary is 0.1 plus 1.96 times 0.0426. So that's going to be 0.1835. And so the way we might write this up would be something like we are 95% confident that the true percentage of all DV seniors staying in state for college this year is, now this number is a difference, right? So that means it's this year minus last year because of the way we said that. So whatever number we get here is how much higher the percentage is this year than last year. So there's two ways you can write this up. You can say that we can't really say the percentage. One way to write this up would be to say, let me erase this. We can say that the true percent, let's just eliminate that word true. I think that's getting in the way here. That between 1.7% and 18.4% more seniors, DV seniors, are staying in state for college this year compared to last year. So you have to somehow include these numbers, but these numbers are differences. So the write-up should specifically state that this is the percentage of that the percentage more seniors staying in state this year compared to last year. Okay, so you have to somehow in your writing get this written so that the direction is included. Okay. It is okay to say this. This is another wording that you can use. If you get confused by that, you could say, we are 95% confident that the difference in percentage of seniors staying in state for college, and then in parentheses, define the difference, define the direction. You could say this year minus last year. So if you show that difference that way, is between 1.7% and 18.4%. So somehow you have to include the direction. You can either do it this way by just referencing the difference, but then defining right in your paragraph the direction, or you can try to bake into the wording like this. All right, that'll be it for the last chapter for Unit 5. So at this point, we're getting ready to review for the entire unit.